Hello everyone! Welcome to my talk on the universality of the cold dark matter power spectrum. My name is Sara Konrad and I'm working with Matthias Bartelmann and many others at Heidelberg University on kinetic field theory, a framework to compute cosmic structure formation analytically. First of all, I thank the organizers for giving me the opportunity to present my work here at the Cosmology from Home conference. And I also thank all the people I work together with. The amplitude and shape of the density fluctuation power spectrum today are determined by two major factors: the initial conditions set after inflation and the growth of structures in cold dark matter due to gravitational interactions in an expanding spacetime. Numerical simulations show that regardless of the shape of the initial power spectrum, the time-evolved power spectrum always behaves like k to the minus 3 for large k. Since cosmic structure formation is highly nonlinear, this universal result is hard to understand with conventional analytical methods. In this talk, I show you in the framework of kinetic field theory that the density fluctuation power spectrum always evolves to this observed k to the minus 3 behavior for large k when particles on straight Zel'dovich trajectories with initially correlated momenta are considered. Today I want to present you three key features of our result. The first is that this power law already arises before re-expansion of structures. The second feature is that this k to the minus 3 behavior persists after onset of re-expansion for all times. And the third, most exciting feature is that this k to the minus 3 behavior is independent on the shape of the initial power spectrum. So regardless how steep your initial power spectrum is, the power spectrum necessarily evolves to a k to the minus 3 structure. But why are we considering Zel'dovich trajectories? First, they are exact before shell crossing, which means that on the large scales they yield exact results at all times. Second, a rigorous analytical treatment across all scales, especially even after shell crossing, is necessary and hard to come by with other theories, but possible in kinetic field theory. And third, Zel'dovich trajectories turned out to be a very good choice as building blocks for the full structure growth in kinetic field theory. And if you haven't seen our talk, Kinetic Field Theory and Introduction, I recommend to watch this one first before you continue watching my talk. As presented in the introduction talk, the full nonlinear density fluctuation power spectrum in kinetic field theory can be expressed as applying two density operators and a perturbation series of an interaction operator on the free generating functional Z0. The generating functional in kinetic field theory contains all information on the solution to the Hamiltonian equations of motion for individual particles. The particle trajectories as a function of time are then given as functions of the initial position, qi, the initial momentum pi, the propagator gqp, and force term f. Now when we consider Zel'dovich trajectories, we assume non-interacting trajectories, which implies that we neglect the interaction operator, and this is equivalent to neglecting the force term in the equations of motion. What we then do is we can choose the propagator gqp such that it corresponds to linear growth factor, which at the end turns out leads to linear growth on large scales. Now note that this choice of the propagator gqp is completely arbitrary in kinetic field theory. We could also choose another propagator, which we then would have to compensate in the force term. So nothing is lost by taking this approximation. Furthermore, we assume Gaussian initial momentum correlations, which means that the correlation matrix CPP of two particles that are initially separated by a distance delta q is given in terms of the initial density fluctuation power spectrum P delta I of k. The general expression for the cold dark matter power spectrum is given as an average of this exponential function, where qi of t and q2 of t are the trajectories of two individual particles. For particles on straight Zel'dovich trajectories, we get in kinetic field theory this integral expression. where you see the initial momentum correlation matrix appearing in the exponent. Let's first look at the large-scale limit, where k goes to 0. In this case, we need to expand the integral for small modes k. And we get the linear power spectrum for large scales as expected. Now let's have a look at the small scale limit when k goes to infinity. In this case, we need to expand the exponent that appears in the integrand for small scales. In this case, up to second order in Q. And the fact that this is the correct way to do is proven by us mathematically in a work to appear. Now note that the first term is independent of Q and proportional to sigma 1 squared third, which cancels the term in front of the integral. The second term, quadratic in Q, contains the Hessian matrix A being proportional to sigma 2 squared, where we have defined the moments of the initial power spectrum sigma n squared. After performing the expansion of the integrand, we are left with the Gaussian integral, which we can easily integrate, and our result is a power law in k. More specifically, as k goes to infinity, our density fluctuation power spectrum behaves like k to the minus 3. Note that the method we applied here for expanding the integrals for large k is closely related to Laplace method, or the saddle point approximation. And interestingly, this result has also been found recently by Shen and Pietroni in the Lagrangian formulation of fluid mechanics. Now let's have a look at the amplitude evolution of these asymptotics. For early times, we have a growth of structures, so the amplitude rises, while for later times, when re-expansion sets in, the structures are decayed again, and they decay like time to the minus 3. And when we integrate this oscillating integral numerically, we indeed observe this evolution of the amplitude. So let's first have a look at very early times. Here we set a equals to 0.04. And you already also see our first claim that the k to the minus 3 behavior is actually present before re-expansion of structures. At a bit later time, a equals 0.05, our amplitude grew a bit, and in this case at a equals 0.065, the amplitude reaches a maximum. Now when we look at times after the onset of re-expansion, this asymptotic k to the minus 3 behavior is still present, as seen here, at a equals 0.1. When we now go to a bit later times, like a equals 0.5, the amplitude dropped significantly. And even later, at a equals 1, meaning today, the amplitude dropped even further. But the k to the minus 3 behavior is still present and remains present for all times. In order to prove that this k to the minus 3 asymptotics for small scales is indeed independent on the shape of the initial power spectrum, we chose a very drastic hot dark matter type power spectrum initially. This one grows like k for small k and then drops exponentially. Linearly evolved, we have this kind of power spectrum. Now when we compare to the result we get from kinetic field theory for straight Zel'dovich trajectories, we see a difference. Now first, for large scales, so small k, our result is indeed equivalent to the linearly evolved power spectrum. But for large k, so small scales, we indeed reach the predicted asymptotics. To summarize our results, we observe a k to the minus 3 power law for the time-evolved cold dark matter power spectrum for particles on straight Zel'dovich trajectories. And this power law emerges even before re-expansion of structures. It persists after the re-expansion of structures, and most importantly, this is independent on the shape of the initial power spectrum. I have shown you today in the framework of kinetic field theory that the density fluctuation power spectrum always evolves to this observed k to the minus 3 behavior for small scales, when particles on straight Zel'dovich trajectories are considered and momenta are initially correlated. Now the interesting question is whether this k to the minus 3 behavior remains valid even for the full density correlation power spectrum by including all kinds of interactions. And this is the next thing we are going to investigate. And with this, I thank you very much for watching my talk. Please visit also the talks by Elena Kotzlikin and Carsten Littek on kinetic field theory. I'm looking forward to meet you in the discussion session. You can also contact me via email or LinkedIn. See you soon!